Hi everyone. In this video, I want to take the opportunity to talk to you about 4 different techniques for handling unbalanced data. Now, unbalanced data is a situation that we can end up in where we are working on a classification problem. To be more specific, an unbalanced data set is a situation where we have an unequal number of samples for our different class labels that are available in our training data. Now, in this video, I want to first illustrate why we want to correct for unbalanced data in the first place, and then outline to you 4 different techniques for how we can possibly treat for unbalanced data. Now, following this, we will go into a Jupyter notebook and there implement each of the 4 different techniques that I will have already described. And then we will compare how well these techniques do on a simple toy data set. Now, all coding shown in this video is done in a Jupyter notebook available on my GitHub. You can find a link to this notebook in the description below. In addition, I also have a blog article on this same topic, so I will also include a link to that blog article also in the description of this video. So why might we want to treat for unbalanced data? Well, in short, most learning algorithms will tend to favor the majority class that is present in our training data over the minority classes. Now we can do a simple thought experiment to illustrate this point. So we can imagine a case where we have quite a severe class imbalance. Let's imagine we only have 2 classes available in our data set where, let's say, 99% of the data belongs to one class. That will be our majority class. And the remaining 1% will belong to the second class, or this will be our minority class. Now, for a learning algorithm to do well against, say, for instance, a measure of accuracy, all that algorithm has to do is just predict everything to belong to majority class. So it will get all instances of our minority class wrong, but it doesn't matter because if we compute, say, the accuracy of this classifier, it will already score 99% accurate. It's misleading. The algorithm is not actually doing any decision making. In fact, it's just spitting out the majority class for anything it receives, but according to its training algorithm, it will have performed quite well because of the nature of the class imbalance. Now that's an extreme example, but even for situations where the class imbalance is not that severe, it can still interfere with the proper operation of the training algorithm. So this is the reason why class imbalance is something that we cannot ignore and that we want to treat for. Now, before I move on to outline the 4 different techniques we can use to deal with class imbalance, just note that in this video, I'm going to be strictly talking about binary classification problems. This is a case where our class labels only consist of 2 distinct values. We can think of this as being 0 and 1. This will just simplify the discussion here. Now, the 4 different techniques are as follows. The first is what we call oversampling. And in this situation, we can sample with replacement from the minority class a number of samples until we get an equal number of samples in the minority class as what we already have in the majority class. So we can see this in the visual that you can see here. So in this situation, the minority class is shown in orange, and the majority class is shown in green. Now you can see above the first block of the minority class, we have these shaded out orange blocks. And this just shows or represents the samples that we have drawn with replacement from the minority class up until we have an equal number of samples for that minority class as we have for the majority. So that's all we're doing. Then we have an equal number of samples in total for both classes. The next approach that we can talk about is called undersampling, and this is the reverse of what we did in oversampling. In undersampling, what we do is we sample out without replacement from the majority class an equal number of samples that we have in the minority class. So here in this visual, we can see the samples that we have extracted out from the majority class is this shaded out block of green towards the bottom of the green bar. And we see that this has the same number of values, has the same vertical height as the minority class that we see that's in orange. And so in this case, we have accomplished the same thing. We have the same number of samples for both the minority and majority class, and you can train your model on that. The third approach we can use is what we call synthetic data, or we can use a synthetic data generator to make up the difference between the majority and minority classes. So this involves training a data synthesizer on the minority class and then using that trained synthesizer to produce as many samples as we want. And in this case, what we do is we generate the number of samples that is the difference between the majority and minority classes. You then add those samples to the minority class, and now you have an equal number of samples for each of the two different classes. The last approach is actually to not modify the training data at all. Instead, here what we do is we tweak the learning algorithm itself. And this is what's called class weights. So we feed into the algorithm weights that are associated with each of the two different classes. And normally, these weights are proportional to the inverse of the frequency of the respective class. So we're going to get a smaller class weight for the majority class, and we're going to get a larger class weight for the minority class. So that's essentially how that's going to work. And this is an interesting approach because it doesn't involve modifying the training data in any way. So these are the four different approaches that we're going to explore here. Now that I've outlined this, let's jump into a Jupyter notebook and begin with the work of setting up our data and implementing out these four different approaches. So now we're in the Jupyter notebook, and we can begin our work here by first running a cell where we will import all the packages that we will need for the analysis to come. So let's just run this cell. And now we can create our data. So as I mentioned already, we're just going to be using a simple toy dataset. And for this purpose, I'm going to be making use of the make classification function that is available through scikit-learn. So here, this data is going to consist of 10,000 samples with a total of 100 features. 10 of these features is going to be informative, and 40 of them will be redundant. Another 40 will be repeated features. Now, as I already mentioned, here we're only going to be working with binary classification problems. So here I specify that the number of classes will be 2. Now, to set the class imbalance, I set the weights for the two different classes to be as follows. So the first class is going to consist of 95% of the data. That's why it has a weight here of 0.95. And the remaining 5% will belong to the other class. So this will be, the first one will be the majority class. The second one will be the minority class. I also set the random state just so that we get reproducible results. Okay, so we can run this cell, we get our data, and now just to simplify our work to come, I'm going to package this all up as a pandas data frame. So that's what I'm going to do in the next cell, along with labeling all the column names, and then I will set our label. So that's what I'm going to do there, and we can just take a quick peek at the data that's produced. So this is what at least the first 5 rows look like, and we can see the column names, and then at the end we've got our label. Okay, and then I'm also going to define the model that we're going to use for this analysis. And in our case, we are going to use a random forest classifier that will consist of 10 different estimators, and I will also set the maximum depth to be 5. The random state will also be specified again, just so that we get reproducible results. So let's run this cell. So the first thing that we actually need to do before we get into the 4 different techniques of handling unbalanced data is to actually set our baseline. So we're just going to run the model on the data as is. And so this will just give us a sense for how much each of these techniques actually improves our model, and will just give us a good starting point for what we can expect to see, or to what degree each technique will actually improve upon our model. So let's just go ahead and do this. We're going to start by splitting our data into X, which is just our features, then Y, which is our label. We're going to be doing a 5-fold cross-validation to measure the performance of our model for all the different tries that we're going to do as part of this notebook. So we're going to do the 5-fold cross-validation, and then I'm going to use as metrics the ROC area under the curve and the F1 score. So this is what we're going to be using to assess how well each technique does. So let's just run this cross-validation on the data as is, and now we can take a view on the results. So here the bottom 2 rows shows us the results on the ROC area under the curve and then the F1 score. We can see that the area under the curve has values that are roughly in the mid-80s or so, but the F1 score is quite a bit lower than that. It's hovering around just above 0.5. So let's see what we can do with each one of our approaches. Hopefully we can improve upon these numbers. Okay, so the first method that we're going to try out is oversampling the minority class. So the way I've implemented this is just in a function here. We have it in this cell. So this function is going to take in as an argument a pandas data frame that consists of our data, as well as a dictionary that is going to specify our minority class. So at the beginning of this function, what I do is I extract out the name of our label column from the dictionary that's provided, and then I use this to split up the provided data based on whether it's part of the minority or majority classes. After this, we do a simple check just to make sure that the minority class was labeled correctly and that we basically see that there are more samples in the majority class than in the minority class. So this is just a simple sanity check. Once we get past this, we can draw the samples from our minority class. So here we're just taking advantage of the sample method that's provided by pandas, and we can sample with replacement the same number of samples as what we have in the majority class. So that's specified here. And then we just turn this on to ensure that we're sampling with replacement. So that's what we do here. And then we return the concatenated data frames that we've gotten from the majority class. So we take the majority class that we've already extracted out up above, and we join to it now the sampled minority that we just accomplished previously. And then that's the data we can use for training. So let's run the cell and now conduct our oversampling. So that runs pretty quick. And now we just proceed as we did previously for the baseline. So we split up our data into X and Y. We run our cross-validation, and we can view the results. So here, we can see right away that our ROC area under the curve is quite a bit better. Now we're in the mid-90s here, and our F1 score has really improved. So now we're in the high 80s. So this is a pretty dramatic improvement over our baseline. This is pretty good. So, all right, so for oversampling, we've already got a win. Let's see how undersampling does. So like before, I've implemented the undersampling technique in a single function. The arguments are the same like before, except now the dictionary specifies the majority class. That's this dictionary here, specifies the majority class instead of the minority class. So like before, I extract out the label column. I split the data based on whether it's part of the minority or majority classes. We do our sanity check to make sure that the minority and majority classes have been correctly labeled. And now I sample out, without replacement this time, from the majority class an equal number of samples as what we already have in the minority class. So that's what I'm doing here. Again, like before, I'm using the sample method that's provided by pandas. So this is pretty similar to what I did before, except that now the Boolean replace is set to false instead of true, and we are sampling out the same number of samples as what we have in the minority class. So that's all we do here. And then again, like before, we return the concatenated result between the minority class and now our sampled majority. So that's the whole function. We can run the cell and now do our undersampling. And now just proceed as we did before. So we get our XY arrays, we do our cross-validation, and we can view the results. So here we can see that the ROC area under the curve is in the low 90s to high 80s. So this is not as good as what we saw previously with the oversampling. And the F1 score is also not as good. So it's kind of fluctuating between the mid to high 70s and the basically mid 80s or so. So this is not as good. When you think about it, this is not too much of a surprise because what we've done with undersampling is we've actually thrown out quite a lot of data that we would otherwise use if we were using the oversampling technique. So because we've thrown out all this data, doesn't necessarily make too much of a surprise that our performance has suffered. The next approach that we will try out here is the synthetic data technique. Now again, this is implemented in a function. The arguments of this function are the same as what we did for our oversampling approach. So it's going to be the data as a pandas data frame, and then we have a dictionary specifying the minority class. The beginning of this function looks very familiar. So we split up our data into minority and majority classes. And then I do a sanity check just to make sure that the labeling has been done correctly. And so now we can move on to making our data synthesizer. Now what I'm going to be using here is the Gaussian copula synthesizer that's available from the Synthetic Data Vault. Now, if you haven't used or if you haven't looked into the Synthetic Data Vault, it's actually a pretty neat package. I recommend that you take a look at it if synthetic data is something that you think might help you out with whatever you're working on. It's really an interesting project, and yeah, it's helped me out quite a lot for previous work that I've had to do. In any case, you can see a simple example here of how it can work. So what we do first is we extract out from our minority class just the features. So I'm going to take from our minority data set just the features, so I drop the label. And then the way Synthetic Data Vault models work is that we have to first extract out the metadata from the data frame that's provided. So we just do this with this metadata object. And then we can specify a synthesizer. And here I'm just going to be using the Gaussian copula synthesizer. And the input argument to this is just the metadata that we just extracted out. We can then fit this synthesizer, and then once we have that done, we can draw out as many samples as we like. And in this case, what we're going to do is draw out the same number of samples that is equal to the difference between the majority and minority classes. So that's all we're doing here. The results are contained in this data frame called synthetic. Then we just add to it a column for the labels. We just assign them all to be equal to 1. So once we have our synthetic data in place, we then return the concatenated results of our majority, minority classes, along with the synthetic samples. And then this is going to essentially result in an equal number of samples between our majority and minority classes. So that's all we've got here. So we can run this cell to define the function and then generate our synthetic data. Okay, and now we can proceed like we did previously, and we can view the results. And these results look pretty good. So here we can see for the ROC area under the curve, we have values that for 4 out of 5 of the folds are very close to 1. So these are really, really good values. And for the F1 score, it's also excellent values. So these are all really, really high, except for the first one. So I have to admit that I'm actually quite surprised at how well this technique worked. My own intuition would have been that this approach would have been a bit too complex to be really effective. My gut instinct would have been more for one of the other approaches that are a little bit simpler. But no, in this case, it has really worked out, and yeah, is actually pretty interesting. It's really nice to see. So now we can move on to our last technique, and that is for setting the class weights. So here we don't actually modify the training data at all. Instead, what we're going to do is redefine our model. So here you can see that we've redefined the scikit-learn random forest classifier. The only change in comparison to what was done above is that I've now introduced this additional argument called class weight. And here we can specify this as being equal to balanced. So internally in the model implementation, it will now assign weights to each of the classes that are based off of their relative frequencies, or the inverse of their relative frequencies to be more exact. Initially, I really liked this approach because it doesn't involve tampering or messing around with the training data at all. But let's see how it actually performs. So we can just run through these cells and see. The results are not really that great. We can see that the ROC area under the curve is in the high 80s to low 90s. And the F1 score here is really not that great. It's actually just a little bit above the baseline that we saw earlier. So yeah, setting the class weights really did not help in this case. It could be that just the class imbalance is too high for the weights to really provide that much of an effect. So that might be a reason why this approach didn't work. But yeah, it's quite interesting to see these results. So now let's do a more visual comparison of the sets of results that we have obtained. So to do that, I'm going to generate some box plots for the set of area under the curve and F1 results that we've obtained. So let's just run through these cells. So the first plot that we see here is for the ROC area under the curve. You can see that all 5 of the different approaches are listed here. So we have our 4 techniques for dealing with unbalanced data, and then I also included the baseline here, so we've got a total of 5. And here, like we already discussed, the clear winner is the synthetic approach. Produced overall the highest values, and also the spread is very small. And so we not only get good results with this approach, but also consistent results as well. In second place comes the oversampled technique. Again, the spread is not that high, and the results are quite good. Below that, the undersampled approach has quite a large spread and is quite a bit lower, along with the class weights. Both have large spreads, and their performance is not as great. You can also see the baseline, yeah, and it's hovering here around the mid-80s or so. When we look at the F1 score, again, we see that the synthetic data, again, is right up there, small spread, so really did well. We can also see that the oversampled approach, also really good, quite high, and then as a minimal spread. We also now are able to distinguish between the undersampled and class weights. So previously, if we go back up, both are kind of hovering around the same point when it comes to the area under the curve. For this particular F1 score, though, we see we're able to make a bit more of a distinction between the two. And yeah, class weights really didn't work out in this particular scenario. Yeah, the undersampled is a little bit better. Now, take from that what you will. I would personally attach perhaps a little bit more weight to the area under the curve, just because these results are independent of the threshold choice. So this is maybe a little bit more insightful. So this concludes the video. I hope you enjoyed going through this material and learned something along the way. If you did, please like, share, and consider subscribing to the channel. Your support is greatly appreciated. Until next time, have a great day, and see you in the next video.